Hi, everybody, and welcome to our live stream today. The live stream today is about the low pressure part of a commercial refrigeration system, which we are sort of taking as the first step in a small series of live streams about commercial systems. With us today, we have Jörg Saar. Could you please? Yeah, hi, there you are. And we have John Broughton. Hi, John. And Jamie Kitchen.
Hello, hello.
Yeah, and we have myself, Jens Andersen, joining from Denmark. Jörg is in Germany. John is in England. And Jamie Kitchen is in Canada. Behind the scenes, we have some of our unsung heroes. We have Morsha Longa from Slovenia, we have David Diaz from Spain, and we have Sujan Sanju from Denmark. To get things rolling, I'm going to, as usual, ask one of these strange questions, and this time I'll take it out on John.
Thanks, Jens.
Man, I'm glad I have to wait for
Because
the second syllable because we all start with J, right? But
yeah,
yeah.
Yeah.
that's right. No, John, you once said something about MOP or KVLs, and I'm going to make a sort of a quick translation of that. The MOP is max operating pressure, and that relates to the thermostatic expansion valve. And the KVL is actually the Danfoss crankcase pressure regulator. So, John, uh, could you please put a few words to this MOP or KVL? What is the discussion?
I'll do my best, Jens. So thinking of an application, for example, if we have we want to cool down some warm carcasses, for example. So, in a slaughterhouse type environment, and we load our cold room with freshly killed carcasses, and we've got a massive heat load there. Now, what we don't want to do is overload our compressor with a high suction pressure coming back to the machine. So then we've got two options. We either use a MOP expansion valve, which basically, as you said, maximum operating pressure. So the valve will basically uh, limit the pressure that is going back to our compressor, or we have the option of using a crankcase pressure regulator. The challenge with either of them is that we want to have refrigeration. We want to start and cool that product in the cold room, but we also need to protect our compressor. Now, on an application such as I've described, the better way to do it would be to use a crankcase pressure regulator, because then we are allowing the evaporator to do its job, as in be filled with liquid and absorb the heat from the heat load within the room. And then the crankcase pressure regulator will just limit the crankcase pressure or the suction pressure that compressor sees as it's operating. So we still get the heat exchange within our evaporator from the heat load. If we had an MOP valve, basically that MOP valve would shut, and you wouldn't get any refrigeration, let's say, taking place within the evaporator. So a KVL is the better way to go.
Thank you.
Hope that's clear.
Uh, I hope so too. But that reminds me of something I forgot to tell you in the beginning. You are very welcome to ask questions. So if you have questions, yeah, exactly, got a question, then please put it in the chats, and we will answer as good as we can. It would be very nice of you to also, if you ask a question, then just state from where you are. That would
Yes.
be good to know. Thank you so
Yes.
much.
Yes.
Um, John, talking about the filled evaporator, etc., etc. Are there any other comments in that respect that we should probably sort of address right away?
If we're talking about the low pressure side of the system, Jens, we've mentioned MOP, we've mentioned the crankcase pressure regulating side of things, and the reason why we want to protect our compressor. Every compressor is made to operate within an envelope, as we call it, which is your basically pressure range and temperature range of that machine. And if we take it outside of that, obviously, if we have a really high suction pressure coming back and we don't do anything about that to limit it, then that compressor is going to pull high amps, and obviously that's bad for efficiency, but also bad for the compressor itself, because then we could start and burn the windings out on the machine. So the reason we do that, and the reason we do that in any part of the system, is to keep the products working in the area or envelope where they should be.
Yeah.
Great.
Yeah, you also see that on low temp systems too. Um, when you have compressors designed for low temp refrigeration, you generally have a compressor shell and piston and valve from a large compressor with the motor from a small compressor inside of it, because it's designed to move large volumes of low pressure gas that has low density. But if you're coming off a defrost or you're just starting the system up, it's the same thing as John said. Suddenly you're going to run out of motor. Your motor's not going to have the capability to move this high mass of refrigerant. And so it's going to literally draw way more current than it's supposed to, because it can't keep up. And as John says, you'll end up overheating the motor. So crankcase pressure regulators, yeah, that's what they're designed for, is to throttle that refrigerant coming back.
Any comments, Jörg?
No. There's only one thing that you already said, Jens. And I just see that many people say hello to us. Thanks to all of you. Hello to everybody. And it's amazing to see where you are from. So some people write where they are from. I've seen Mozambique. I've seen Israel. I've seen some others. That's really good to see that you are from so many places around the world. India, somebody said that. So thanks for joining here. Happy to have you here. Thank you.
Yeah, thank you so much. It's a bit slow on questions, but maybe we could have one of the questions coming up for you guys. A question to the audience. That would probably be good if we could have Moshe. Could you please post one of these?
Oh. Size in a receiver. Do you want me to try that one? Yeah. Generally speaking, what I remember is that the receiver on a refrigeration system, or air conditioning system, or whatever it happens to be, what you want to be able to do is have all that refrigerant that's the system is charged with fit into that receiver. And you can basically store the refrigerant in there. You can pump it down. So as a safety, it has to be sized large enough to hold the refrigerant. And this becomes important if you have, remote evaporators, where your evaporator may be located a certain distance away. You have to be able to hold all of the refrigerant that would normally be in the evaporator, the condenser, and also in these long runs of pipe. So you'd have to be able to hold the entire charge. Now, what you don't want is you don't want a receiver 100% full of liquid, because liquid undergoes what's called hydraulic pressure rise. Whereas when you have vapor, you can compress that vapor, but you can't compress a liquid. So you always want to leave some space on top of the receiver or in the receiver for that liquid to be able to change temperature and expand. And we always used 20% of the charge weight as a rule of thumb. In fact, when you buy a jug of refrigerant or even a jug of propane, a lot of times they will say the maximum fill rate is 80%. So that always leaves you 20% vapor space on top to allow for expansion of the refrigerant, should it increase in temperature.
Yeah, agree to that. That's a really good rule of thumb. So let's say you have 8 kilograms of refrigerant, or let's recalculate that, maybe 6.5 liters. So your receiver needs to be 6.5 liters plus 20% of that.
Yeah.
So around 8 liters then. That's what
Mhm.
your receiver should have, so that,
As a
as Jamie
minimum.
said, you can store
Mhm.
all your refrigerant in the receiver.
Mhm.
That sounds great. That's all fine. But now, over time, not over time, but now you more and more see a challenge with all of that. Just have that in mind. The rule of thumb still applies, but there is a challenge coming up, and the challenge is flammable refrigerants. Because with flammable refrigerants, you want to minimize the charge as much as possible. And quite a bit of the charge is hanging out in the receiver. So you try
Mhm.
to minimize that charge, you get smaller receivers and so on. There is going to be a conflict of interests. One is that you make your receiver big, you get all your charge into the receiver easily, no problem. The other one is you want to make your receiver small to reduce the charge of flammable refrigerants. So
Mhm.
with flammable refrigerants, we run a bit into a conflict here, a conflict of
Yeah.
interests.
Yeah. That's interesting because you see that in a lot of other things as well, where people say, "I'm going to go with a larger size filter dryer for safety." Well, that filter dryer has to be filled up with refrigerant.
Hmm.
And in smaller systems, a filter dryer can be a sizable um, volume compared to the rest of the system. And as York says, if you got a flammable refrigerant like R290 and you have an oversized filter dryer, suddenly the refrigerant that would normally be in the evaporator or condenser is now sitting in either your large filter dryer or oversized receiver, and it's not be able to do the work that it's supposed to do. That's a really good point, York. I never thought of that actually.
Yeah, there are some points coming together. That's the challenge when we talk about a rule of thumb. They quite often work fine in general, but then if you go to specific cases and so on, you really need to pay attention to not only sit there and say, that's my rule of thumb, that always works. Well, it's a good first shot quite often, but then you need to go into details sometimes.
Hmm.
Yeah, I can see we get a few questions about MOPs, MOP valves, etc., etc. Maybe could we have one of you guys asking, or sorry, answering the the, um, the question from Manoy?
Can MOP expansion valves help to avoid surging in chillers?
Mm.
Now I'm not totally clear what is meant by surge, because that might have a few meanings. One is if that is a turbo chiller, that might
That's what I'm thinking.
be a surge condition. Would it be that? What do you think, Jamie?
That's the way I've always interpreted it. Was surging was always on centrifugal turbo type compressors, and you can tell as soon as it happens because you can hear it from a mile away, and it is a problem. I do not think an MOP valve would be able to solve that. For one thing, its reaction time would be way too slow. All it's really doing is limiting the amount of opening that's occurring because it runs out of liquid in the bulb. So it's based on temperature and pressure. So if it's, you know, so
Yeah.
I don't see how that would help a
No,
surge in a centrifugal chiller for sure.
no,
It
me
it
me
might
neither.
it might even make it worse.
Yeah, because usually they don't
Um,
happen under full load, does it?
no, no,
No.
exactly.
Yeah, because
Exactly.
making it worse, because if you would have higher evaporating temperature, which would be possible, then the MOP limits the injection, and all of a sudden you you get a lower pressure there, a lower evaporating pressure, and you might run into a surge condition because of that. That is
Mm-hmm.
possible. Yeah,
Mm-hmm.
I wouldn't say an MOP valve solves the surge problem on a turbo chiller.
Yeah. But your Jason Fraser has a good question here. If you want to maybe take a try that one because it says how much less does it open compared to a regular valve? Um, what do you
Oh,
think?
okay. Well, it opens as a regular valve. because it is a regular expansion valve. The only thing that happens when you come close to the MOP, to the maximum opening pressure, then the valve will no longer open further. And from a certain point onwards, it will not open at all. So below that maximum operating pressure, if you are low enough below that maximum open pressure, then it works as a standard expansion valve. No difference in opening, nothing whatsoever. It's just when you come to that maximum operating pressure, then what happens in the bulb of the expansion valve, all the charge you have in that bulb has evaporated. But your pressure in the evaporators continues to increase. So the pressure in the evaporator is put back to the expansion valve via the external pressure equalization. And that pressure in the evaporator that continues to increase presses below the membrane of the valve and presses the membrane upwards. And that's how the valve closes then, because there is no counter force available, which usually comes from the pressure in the bulb to press the membrane down to open the valve again. Because all the refrigerant in the membrane, all the charge in the membrane has evaporated. It cannot build up additional pressure. And that's why the valve will not open. But as soon as you are enough below that point, let's say 5 Kelvin below the maximum operating pressure, your forces are in complete normal operation. The bulb is generating pressure as it should, and the evaporator is generating pressure, and you have your very normal operation there. I hope that answered the question. So you can get 100% capacity from an MOP valve when you are a bit away from the maximum operating pressure from the MOP.
Yeah.
Great.
And if you select them on temperature, right? What's the maximum
You
temperature that
select them
you want?
on temperature or pressure. I mean, it's the
Okay.
same thing, kind of.
Yeah.
If you say
No, I understand.
it's 15 Celsius, you can calculate that into a pressure, and you get a certain pressure, whatever that is in PSI or MOP. That depends then on your refrigerant you are using. And as soon as you come close to that point, the valve is no longer able to maintain a superheat, because all the charge in the bulb has evaporated and it can no longer open. And that's why it limits then the injection, and that's how it limits the pressure in the evaporator.
Hmm.
And as you
You
say,
know.
you select it according to pressure, temperature, let's say temperature, and you select it in a way that you do not overload your compressor. Let's say your compressor is able to do 15 Celsius evaporating or 10 Celsius evaporating. You have a 15 Celsius MOP, so your evaporator will not go higher than 15 Celsius as evaporating pressure. You do not overload your compressor during running conditions. During startup, the MOP takes a bit of time before it can bring down that evaporating pressure. It's not as fast as the KVL John talked about in the beginning.
Good point.
Yeah, we get another good question from about the MOP and how to work with it. It's Tottenham who's asking, what is the do's and do nots when it comes to MOP usage? Can you, again, rule of thumb again? What, when, where, how, why?
Yeah, I mean, if you have an MOP valve, first rule of thumb is you need to be away 5 Kelvin approximately for it to go back to normal operation. So let's say your MOP is 15 Celsius. Between 10 and 15 Celsius, you see an effect already. So below, as if the MOP is 15, take 5 away, you are at 10. So below 10, it works as a normal valve. Between 10 and 15, you see more and more the effect of the MOP. That's the first rule of thumb. Second rule of thumb, if you have an MOP valve, very important that you make sure that the bulb is not getting warmer than the valve. Because if that happens, your charge, if your bulb is a good deal warmer than the valve, your charge migrates into the valve. And then the bulb has no influence anymore whatsoever. It stays in the valve, in the head of the valve, and your control is gone, your superheat control later on.
Yeah.
And then the rule of thumb is typically about insulation of an MOP valve. There are a lot of discussions, but it helps when you do not have an insulation on the MOP valve. Third rule of thumb, don't put it into the cold air stream. That valve.
Yeah. Yeah. You're going to see that mostly on outdoor units too, right? Where if you have a cooler type scenario and then you have a place like where I live or whatever, where it gets really cold in the wintertime, you have an outdoor unit, you want to make sure that valve is not sitting in, -5 degrees Celsius air when the suction line is, 8 degrees Celsius or something like that. That would be a situation. Have you guys ever heard this one, that you never put an MOP valve in a system that also has a crankcase pressure regulator? The two of them, it's either one or the other, but you never put the two of them together because it's not a matter of two is twice as good. They're going to hunt or fight each other, would they not?
I would say exactly that, Jamie. I'd say that they would fight each other.
Yeah, I just remember somebody telling me that years ago. Never ever mix the two of them together, and it always stuck with me. So, yeah.
It
Yeah.
might work, but I wouldn't do it.
Yeah. Yeah.
Rule of
No,
thumb,
I understand.
maybe not.
Yeah. Let's see. Yeah, we are. There are no. Well, maybe it's because we have, or you have explained it quite nicely. But the questions are about. About MOP as sort of seized. But Ahmad Ali, he has a question about tandem compressors. You can see it here on the screen.
Can I use tandem compressors in place of a single recip with the same TXV?
I can. You want me to give a stab at that one?
Yeah, you want to go, or should I?
Yeah, I can go ahead and that.
Yeah, just go.
Yes, I mean, if you're looking at a tandem compressor, really what they are is they're handling a common suction. And so a big concern with the tandem compressors sharing a common suction as discharge is more on the oil side, managing your oil level and scheduling your compressor start and stop so that you maintain correct oil level in both compressors rather than having one hog all the oil. But in regard to that, when you're feeding let's say a single evaporator in a it could be a air rooftop unit, it could be something else where you have a common evaporator, you're feeding a with a single TXV, and you have two compressors drawing off of that evaporator through a common suction. From the TXV standpoint, it really doesn't care or know what's on the other side of that evaporator. It is essentially injecting refrigerant into that evaporator, and it's probably going to be a multi-circuited evaporator, so it has a distributor. It's going to be an externally equalized TXV that's measuring the pressure and the refrigerant temperature, if you want to call it, at the outlet of the evaporator before in a common suction line. So it doesn't see what's further down. It doesn't realize you're eventually going to split that. All it's going to see is a change in pumping capacity. So if you drop one of the compressors out and you only have a single compressor pumping, really what that means is suddenly your load drops off. And that's why you dropped the compressor to begin with, was because your suction pressure started to drop off. It's just going to throttle close to meet that low load. It's going to sense a drop in superheat. It's going to sense an excess amount of refrigerant boiling in the evaporator. And so it is just going to drop, it's just going to throttle closed to maintain the correct amount of refrigerant feed to meet the new pumping capacity. That's going to happen in the evaporator. So you start with a drop in load that's going to drop your suction pressure. You now don't have enough load to boil enough refrigerant to feed both compressors, so your suction pressure is dropping. All you're going to do is drop one of those compressors, just to help balance the amount of refrigerant that's being removed from the evaporator because your load fell off. That's all you're really doing. And then, of course, the opposite is true: is once you introduce a higher load, the suction pressure starts to rise because you have too much heat, you're boiling too much refrigerant, you're producing more vapor than one compressor can pump. So you just basically bring the second evaporator on, or set the second compressor on, and to meet that. And with that, you're going to get a drop in pressure. But from the TXV standpoint, all it's doing is just reacting to the load. That's all. Guys, you want to add something to that?
I'll just add one comment, Jamie, which is something that I get asked a lot. There is a misconception, I think, in the industry that the expansion valve dictates your evaporating temperature.
No.
And that is completely incorrect. It's purely the balance point between your compressor and your evaporator, or evaporators or compressors, the match of those two that will actually determine where you evaporate at. And my camera's gone a bit fuzzy, so apologies for that.
I just thought it was my eyesight because I'm old, but yeah, okay, I guess I'll take your look, I'm clear, man. Look at that.
Yeah.
So there you go. Yeah, I mean, we could probably spend a whole show talking about balance points because it is probably one of in fact, that is a rule of thumb, is that the compressor, or the capacity of the evaporator and compressor, is really what determines, the range your evaporator is going to work under, right? So that's a really good point. So Jens, what else you got, man?
Yeah, I think we have a question from C Legit. There you go. I take this as a follow-up on what we talked about before.
No,
Okay,
I
let
think
me take that because
Jörg.
it seems I was not really clear on that one. No, I don't want to say you should not insulate the bulb. What I want to say is it is okay not to insulate the valve. And maybe that's an advantage on an MOP valve, not to insulate the valve, because then the upper part, the thermo element of the valve, will not get that cold. You should insulate the bulb, no matter whether that's an MOP valve or not. A normal valve or an MOP valve, please insulate the bulb.
Yeah.
The reason is that the bulb should measure the temperature of the pipe, not be influenced by the ambient. That's why you should please insulate the bulb with the pipe. And the valve itself, the top part of the valve, can be not insulated, or the complete valve can be not insulated. That's okay. But the bulb, please insulate that.
Okay.
Yeah. There's another question coming up from Juan, I think it's pronounced, about defrosting.
That sounds
Anyone?
like a John question.
John
You
question,
think so?
okay.
You think so? A typical cold room question. What do I prefer?
This should be fun.
Yeah, it should be fun. Personal opinion, and this is what we see in the commercial world generally. If it was a walk-in freezer, generally it's electric defrost.
Yeah.
For simplicity, for cost, for everything else. Do I prefer that, or do I prefer hot gas? Hot gas is way more efficient than electric.
Yes.
Way more efficient. So from an efficiency standpoint, yeah, it's much more efficient. The only challenge you have on a one-to-one system, so one evaporator, one compressor, is eventually, and it depends how much hot gas you need to defrost the coil, but eventually you will run out of hot gas. So it all depends on how long you want your defrost to last for. Is it 5 minutes, 10 minutes, 20 minutes? If it's sort of 15, 20 minutes, you will run out of hot gas from your machine eventually.
Yeah, because you got nothing making gas, right? So,
Yeah, exactly. So that's the choice. But hot gas is much more efficient. And a comment that Jörg said the other day when we were having a discussion is, it doesn't have to be complicated. You just need to make sure that the amount of hot gas that you generate within that period of time is enough to do the job. And then look after your compressor. Make sure we're not going to cook the machine.
Yeah, because you mostly see hot gas, from my experience, John. You mostly see hot gas in multi-circuited like supermarket systems where, let's say you've got eight evaporators, and one or two will be scheduled to go into hot gas, and you limit the number of circuits that can be in a hot gas at one time. Do you not? Exactly for that reason.
Yeah. And there is a rule of thumb, as we're talking about rules of thumb, was two-thirds and a third. That's what I was brought up on, at least anyway. So if you had, let's say, 3 machines, you would run 2, and you would generate enough hot gas, 2/3 and a third, to so if you had 3 evaporators, let's say, you could have 2 running in the system to actually produce cooling, and then the third one would be on a hot gas defrost. So you would always generate enough hot gas from that.
That's interesting, because off the top of my head, I would say, the best time to do your defrosting is when, loads are low, you don't have a lot of demand on your coolers and stuff like that. But that's kind of work against you, right? Because if you don't have a lot of evaporator feeding going on, you're not going to make a whole lot of hot gas either, are you?
No, exactly, because we've got to remember that we take heat energy from inside our cauldron and we expel it on or through the condenser. So that's our hot gas. Obviously, you've got the heater compression from the actual action of your compressor, but you want to generate heat, and you take heat from your cauldron or the product within your cauldron, let's say.
And that's coming back to efficiency. Of course, if you have a system with several evaporators, and as John said, let's say you have 6 evaporators, 2 need defrost or defrosting, and you defrost these 2 evaporators, the other 4 are running. Well, then you get your defrost completely free of charge, because your compressor is running anyway, or your compressors, depending on how many you have, they are running anyway. So that's a completely free of charge defrost. You would throw the heat away otherwise via the condenser. Now you use it to do the defrost.
That's a really good point, actually.
Yeah, there was a rule of thumb that I'm trying to remember, how much less energy hot gas uses compared to electric, but I can't remember what it is now.
Well,
is it like based on degree days and humidity levels?
No,
Something
it
really
was
complicated.
like you need 40% less energy for a hot gas defrost, because it's more efficient, because you're putting hot gas within the pipes rather than trying to heat it up from the outside, so to speak. Plus, when you heat it up from the outside, you are trying to heat the pipes from the outside, but you're also heating the air within the cold room as well.
Yeah. Okay.
But I can't remember whether it was 40%, 60%, but it was somewhere around that sort of
well,
figure.
For our listeners out there, if you know, feel free to throw in a link or something to that information and make it available. We'd appreciate it.
Yep. That would be great. Definitely.
Let's jump a bit. We've got a question about CO2 transcritical operation here. Let's see if any one of you guys have a good answer to this one.
Capacity control for minimum operation. Gas ejector parallel compressor VFD. What is VFD controlled? That's probably variable frequency drive. Okay,
yeah.
good. Yeah, got it.
Yeah.
Sorry.
That's a heck of a question.
I can start,
I don't know if you can answer
if you
that
guys
here.
want.
Yeah, go Jörg.
That's okay with you.
Yeah, go ahead, man.
Well, recommended capacity control for minimum operation. There are of course 2 or 3 capacity controls. One is the control at the evaporator, but that works as it just works. I mean, let's say you have a CO2 system, transcritical CO2 system, several evaporators in parallel. and then only one of them needs cooling. So that evaporator is controlled just very normal. There is an expansion valve, it is doing superheat control. But now you have a system that has 10 evaporators and now only one evaporator is in operation. Then your system, your complete system, is at minimum capacity. You have only 10% of the system capacity. And now there is a bit of a challenge because you might have 3 compressors. One of them is variable speed controlled. Can you go down to 10% of the total system capacity? Maybe. That might be possible. So that would be what you would try to do, to reduce the compressor's capacity to the point that you need, in this case to 10%, and then you keep only one compressor running at a low speed. That's what you would do. If you would have a gas ejector in that system, the flow of gas on that minimum capacity is for sure too low to provide a good ejection operation. Your ejector needs a certain minimum gas flow to provide sufficient operation capability. Your gas ejector on that minimum capacity will not give you a real advantage. That's just as it is. But you still can operate the system with that one compressor on a low speed. It keeps running. The good thing is then your gas cooler is probably pretty cold because you have only 10% capacity on the gas cooler as well. And your system efficiency is still acceptable, even without the ejector running, because your gas flow is simply too low that the ejector can give you an advantage there. Hopefully that answered the question. I don't know. If not, please post a new one or an additional one.
Yeah. Meanwhile, we got a question from Silish Damali. I'm not sure I pronounced that name correctly, but anyway, it's about the filter dryer. Anyone?
That's a good question.
John, you go.
Yeah, I'll go. Of course, the normal rule of thumb, and I'm joking here, is we line size it because that is what
with your solenoid valve
99%
too.
of everybody does.
Yeah.
And in probably 99% of cases, there or thereabouts, it does its job. You size a filter dryer on the amount of refrigerant that is in the system to dry that refrigerant. So a too small filter dryer, obviously it will, if there's a lot of moisture in that refrigerant, it's going to get chucked up quickly and then not do its job. If it's too big, yeah, you get obviously a pressure drop through the filter dryer. And then coming back to one of, I think it was your comment, Jörg, about the type of refrigerant and receiver size. Obviously, if it's a way too large filter dryer, then you've got that shell volume full of liquid. So that will actually increase your charge size. So it is a balance between doing what it's meant to do, dry the refrigerant, remove the moisture, but also not be too big so that we're actually having a charge that is, let's say, larger than it should be.
Yeah. And that's,
Yeah,
I
because
totally agree. As you said,
yeah.
A lot of filter dryers are sized according to the line. Well, I mean, there are different filter dryer sizes, shell sizes, coming with different connector sizes. So you still have, let's say, 1/2 inch line, and you still can have different shell sizes. And quite often, then somewhat in the middle, what's available. There's a small shell, a medium-sized shell, a large shell. Usually, the medium-sized is then used, and somehow that typically fits. That the filter dryer has enough drying capacity for the amount of refrigerant. That quite often works. Yes.
Yeah.
The good selection is you check how much kilograms of refrigerant you have, you check how big your shell should be, and then you select the right connection size. I totally agree, John.
Thank you.
Yeah, because the size of the connection determines the amount of tonnage or capacity that can flow through it,
Yeah.
right? So you got to be careful, as John says, how much is refrigerant in the system? If you've got a 10 kilowatt system and it's a package units where everything is close together, it'll have a much smaller refrigerant charge compared to a split system with a remote condenser with remote evaporators, long line runs. You can have substantially more refrigerant charge. So you can have the same dryer with a, half-inch connection, whatever it happens to be. And from a flow standpoint, it'll handle 10 kilowatts or 13 tons or whatever the heck it happens to be. But it's going to run out of drying capacity if you get a moisture issue with some of these longer line sets because you just have too much refrigerant charge.
Yeah, and a lot of that, Jamie, is obviously dependent on the installation, how well the system has been,
Oh, yeah.
let's say sealed, so we don't
Mm-hmm.
have too much moisture in the system, how well the vacuum's been done. So there's a lot of factors in there that actually, can compound the situation. And then if something is made in a factory by an OEM, for example, then their systems will be, let's say, very good regarding the vacuum procedure, short pipe runs, etc. So maybe that is as you say, a smaller shell size.
Mm-hmm. Mm-hmm.
Yeah. Got
Jens, what do
another.
we got?
Yeah, we have a question
Yes.
again from. We have a question from Totmabote Simbine, also related to the filter dryer.
Okay.
Okay.
Anyone?
Is it safe to run? Oh, that's very simple to answer. No.
No.
Yeah.
No.
It's not. Even a small air conditioning package, it would not be safe. I know there are a lot of discussions going on where somebody says, "Yeah, but come on, I don't need a filter dryer. We work really clean. We have factory made units and so on. We don't need filter dryers. There's no dirt in there. Come on." Are you sure you can exclude that completely? Are you sure you can exclude that the vacuum process was not perfect, that you don't have a little bit of humidity left? Are you sure that you can exclude that the refrigerant is perfectly dry that you put in, that there is no humidity in the oil of the compressor because it was
Mm-hmm.
open for a few minutes? I mean, putting a big system on risk by saving a few euros for the filter dryer, I don't think that's a really good idea.
Yeah, I
Yeah.
don't see the upside to that. You know what I mean? Eh, what's the benefit of not doing that that would outweigh any of the risks? Unless
Yeah,
you're just doing an install that's, install and forget where, you install it and then you're right off into the sunset and nobody ever sees you again, right? I mean, eh, as Jörg says, with the next person that comes along and opens that up and then replaces a component, there's no filter dryer on it. So, if they don't put one in, then again, it just compounds the issue. And with POE refrigerants, any moisture is what's going to cause acid problems, right? It's the moisture that is the issue and any other contaminants, So if you plug a TXV up, right, or you fail a compressor, that's a very expensive repair, right? And so the customer is going to be out a lot of money just because somebody decided to save a few euros.
Yeah, that's a good point, Jamie. And I've got a slide that I use when I do training. And basically, if you take your compressor as 100% cost, the cost of a typical filter dryer is actually 2% of the
Mm-hmm.
cost of the compressor.
Mm-hmm.
So you're
Yeah.
saving, as you say, pennies to safeguard your compressor.
Mm-hmm.
I think we have a question from Narendran Susindran.
Mm-hmm.
Hope it's right.
I'll take that one, Jens, if that is
Yes, please go
okay,
ahead.
because I spent quite a bit of time on cold room roofs with expansion valves over the years. Approximately a meter, yeah, no issues whatsoever. I'd be interested to hear actually from the group whether 1.5 meters or 2 meters would be the sort of maximum. But I've happily worked on both thermostatic and electronic valves that have been, let's say, 1 meter, 1.5 meter from an evaporator, and had absolutely no issues at all, so long as that expansion line from the valve is very well insulated as it goes
There you
down
go.
to
That's what I
the
was about to add there. Yeah, you don't want
yeah.
to be picking up external heat in that area
No,
there.
no, because obviously as you expand the liquid through your expansion valve, then it's going to pick up heat. So that line from the valve down to the distributor on the cooler needs to be well insulated. And I don't mean a little bit of Armorflex tape. I mean a good 3/4 inch wall insulation, just to stop, as you say, picking up any heat, because otherwise it becomes very inefficient. But I'd be interested from the group here and also people online, what's the longest length of expansion line you've ever seen on a system?
That's a good
Yeah,
question.
1.5 is probably about what I would say.
Yeah.
Off the top of my head, I'm just thinking of some strange, installations I've seen, but they're mostly chillers in that. And even then,
Yeah.
I'm running the tubing through my head, following the insulation, and I don't think 1.5 meters. I don't think I've seen much that'd be more than 1.5 meters.
No, I would say, I mean, generally the expansion valve is on the roof, line comes down into the cooler. So you're talking 1 meter deep cooler. That's a pretty sizable cooler.
Yeah. As you guys say, feel free to answer in chat what you've seen, but I'd love to see some pictures of that if somebody's got something else. But then
Yeah,
again,
definitely.
one-offs aren't really a rule of thumb. I've seen, TXV sensing bulbs uninsulated sitting in the sun, right? I would never call that a rule of thumb, right? But
Yeah, it's just bad practice.
yeah,
Agreed.
bad practice. Yeah. Does anybody have any thoughts on superheat? Because the funny thing is that I get questions a lot of times on what should the superheat be, and this is one of those ones where I kind of bite my tongue in the sense that I'm leery of putting out an answer. Now, most of the time, in air conditioning, it's a little bit different situation because the amount of superheat you're going to see on especially smaller air conditioning systems is pretty much 100% dependent on the humidity in the space, right? And you can pretty much tell how much humidity is in the space based on almost your superheat. Where if you go up, 7 to 10% humidity in a space, you can actually add a couple of degrees of superheat because that latent load is additive, right? I mean, your space temperature in air conditioning doesn't change a whole lot. You don't run your space down to 5 degrees Celsius. And if you did, well, there's usually a problem, right? It's anywhere between 20, 22 degrees, 23 degrees Celsius. So the sensible side doesn't make a big difference in the load. However, you start dumping latent heat into the space because you have a hot, humid day as opposed to a cool, dry day outside. And suddenly the amount of opening of that TXV that's required to meet that humidity is going to be completely different. Now, John and Jörg, I'm not as familiar on the refrigeration side. What do you guys have any rules of thumb for ranges, not a specific value, but ranges of superheat maybe that you should be looking for?
Yeah. There is a factor, and then you are really pretty good if you use that as a rule of thumb, because many air coolers are built for that factor, and the factor is 0.65. Now you wonder what to multiply that with. Well, the difference between air, the temperature difference between the air inlet into the evaporator and the evaporating temperature. So let's make that very simple. Let's assume you have 10 Kelvin difference. Your air temperature is 0 degrees. Your evaporating temperature is -10. You have 10 Kelvin difference. Now you multiply these 10 Kelvin by 0.65 and you end up at 6.5 Kelvin. That's a really good target superheat for this specific evaporator then. So it's not in general any evaporator. It really depends on that temperature difference between air into the evaporator and evaporating temperature.
Mhm.
That temperature difference times 0.65.
And
Then,
that would be the superheat leaving the evaporator then, correct?
sorry, come again? So,
That would be the superheat leaving the evaporator at your evaporator outlet?
yeah, that's
Yeah,
the
yeah.
superheat
Okay.
of your
Yeah.
refrigerant leaving the evaporator.
Yeah,
Yes.
11, 12 degree F superheat. Yeah, that's about right.
Yeah. So if you have a large temperature difference, let's say 20 Kelvin, your air comes in, your evaporating temperature is 20 Kelvin below air temperature, then you would go for a 12, 13 Kelvin for 12, 13 Celsius superheat. Yes.
Okay.
Yeah, yeah. I mean, when you talk a range, Jamie, a lot also depends if you've got an electronic valve, for example, which you can run a tighter superheat, or
Oh,
a
yeah.
mechanical valve, which would obviously be a bit wider. But there's
Mhm.
also that other thing that I always think about when I'm on site is that if you've got 1 meter of suction pipe between the end of the evaporator and the compressor, I'd always run at a slightly higher superheat
Yeah.
just to
Yeah,
be
because
sure there's no
you have
yeah,
no
no
absorption if anything goes wrong.
yeah, we don't want any liquid coming back to the compressor.
Yeah. Can I
Whereas if
sell
you
you a
had,
suction line accumulator?
of course you can, of course you can, but if you had a 20-meter suction line, then
Yeah.
you've got a little bit more, let's say, safety factor, and you could probably run a little bit lower. But as the main thing is, we don't want to get liquid back to that machine.
Yeah,
Sorry,
if we can all
compressor.
help it for
That
sure.
was,
Yeah.
And
Yeah.
then maybe to add one more rule of thumb, whenever I hear on a commercial refrigeration system, let's say an air cooler for a cold room, a larger cold storage room, whenever I hear that somebody wants to reach superheats below 4 Kelvin, I get nervous.
Yeah. Especially with a
yeah,
mechanical valve. That's a tough one.
Yeah, you shouldn't.
yeah.
I mean, that's a real challenge. It is possible, but then that's no longer a rule of thumb to just should work. Then you really, really, really need to go in the tiniest little details.
Yeah, yeah. There's a good comment actually that's come on the
Yeah.
chat from Daniel Webb. Target superheat is between 5 and 7. I would say you're there or thereabouts, Daniel,
Mhm.
on that one.
Mhm.
Yeah.
Obviously,
So
depending on the
lower temp
application.
systems can tolerate lower amounts of superheat, can
Yeah,
they not?
yeah. Yeah. But then you've also got to be careful of if it's let's say a very low temperature, you can actually almost run out of superheat. It's very hard to generate superheat at a very low temperature.
Mhm.
You can get like a sleeping evaporator syndrome where you can't generate enough heat within the application to actually get the valve to do something.
Mhm. Yeah, I mean that's where you start to get into that low superheat. I think to me that would be where the electronic expansion valve would come in, supporting a minimal stable superheat curve for the evaporator because it's going to try and push that superheat down by staying open as long as possible. You don't have to worry about the you know, superheat spring having, any issues or things like that. I don't want to get into the details of it, but that just screams, EEV, electronic expansion valve to me.
Yeah, definitely. Actually, that's a good question for Jörg. What is the
I
no,
need to go.
I'm just thinking of when we mention about things like that on a typical thermostatic expansion valve, a two-ton valve. What's the stroke of the push pin? Is it like 0.6 of a millimeter or something? I can't
Yes, in
remember
that
the
range,
yeah
0.4 to 0.6 millimeters.
That's so small.
That's what the pin moves, and that's what the orifice in the expansion valve moves.
mm, mm.
Not
Yeah, it's
yeah
more than
incredible.
that. So
which
that's
Not a
not a
lot.
lot.
No.
And with that little bit of movement, you have your full control range, right?
Yeah,
mm,
yeah.
yeah
Yeah.
Um, I
Ac-
do know that in specific applications that are low temp and the customer wants to, push that superheat as low as possible. And low as possible is an important part here because they're not saying I want this amount of superheat. They're saying I want to push it as low as possible while maintain, a stable evaporator. I don't want it hunting. And you can come up with different bulb charges that have a lower, static superheat, opening superheat, whatever you want to call it, setting than say a traditional. But again, you're putting these things in a situation where you can test them, you can prove they're stable. And a lot of times these valves, they may not even have adjustable superheat on them because, they're fine tuned to the point where they're designed for specific loads. They're going to behave in a certain way. But there's not a lot of flexibility there. You suddenly just couldn't change the product or the loading of the freezer or any of these kinds of things. You're very limited in what you can do with these. But again, they're very fine tuned.
I totally agree. And you always need to remember, if you fine tune something like that, you can do that in serial production, for example. If you always have the same valve, the same evaporator, the same compressor, the same system, because then you can fine tune it to this evaporator. If you go for a different evaporator, that even the evaporator might not be stable. There is the MSS, and we could talk about that for quite a long time. The minimum stable superheat, that's an evaporator based thing. The valve has nothing to do with that. There is a certain minimum superheat. Below that, this specific evaporator is no longer able to give you a stable signal. You cannot control it down there.
Correct. Yeah.
And that means for some evaporators, if you go below that point, and that's a different value for every different evaporator design, you are no longer able to control that thing. And then just a final remark from my side, electric expansion valves, going down there quite a bit. I had a situation where somebody controlled 1.2 Kelvin, extremely stable all day long. And I said, you don't control anything. Your evaporator runs completely wet.
Yeah, flooded, 100%.
The only thing that you measure is the tolerances of your sensors, right? So it was completely wet, and you just had the tolerances of the sensor. Because you do a bit of a calculation, you can easily find out that your pressure transmitter and your temperature sensor, they have certain tolerances. If you add them up, and if you're unlucky, you measure a stable superheat of, let's say, 1.2, 1.5 Kelvin. But you have no superheat. It's stable wet. And then you only measure the tolerance of your sensor.
Yeah, because I don't know any evaporator that's stable below 4 Kelvin, 3.5, 4 Kelvin, at least off the top of my head anyways. You know what I mean?
Yeah.
I've worked with enough minimum stable superheat algorithms that I can tell you that if you can hit 4 Kelvin, you've had a really good day.
Yeah. There's a comment actually from Daniel saying he was taught never go below 5K.
Yeah, and that's a pretty safe bet.
That's a good approach.
Yeah.
Guys, I think we are heading towards the last question.
Oh, it's late. We're talking for
The
an hour
final
already.
countdown.
Totnaborta Simbine is asking about the minimal oil level on a trio compressor.
It's the same as a single compressor.
Yeah.
Yeah. 3/4 of a sight glass.
Yeah.
3/4 of a sight glass.
Yeah.
Well, it's funny because if the oil is visible and it's not moving heavily in one direction or another, that puts my mind at ease because it's going to fluctuate, right, depending on different loads and that. But if it's somewhere near the middle of the sight glass and it's not going either above the sight glass or below the sight glass, I wouldn't lose any sleep over it. It's when one of those compressors suddenly either is completely full of oil or completely out of oil. In other words, you can't see it in the sight glass. That's when I start to worry, to be honest with you.
Agree. And John said 3/4. No, what did you say? 2/3.
Two-thirds. Yeah.
2/3 of the
Three-quarters,
sight glass can be empty, so that the lower third needs to show oil, right?
Yes.
In every single compressor, not only one compressor of the trio, but every compressor has to have at least 1/3 from bottom up of the sight glass. If you are below that,
that's a good
you're
practical tip to
running
follow.
close to having an oil issue or an out of oil issue.
Yes. Yeah.
Yeah,
Then
no,
the
that's a good
compressor
practical
makes
tip. because you can drive yourself nuts trying to fine tune that. But again, it's not going to. You're always going to be hitting a moving target, right? Because a system is not stable, especially if it's got multiple evaporators. It's never going to hit a complete point of equilibrium. It's always going to be mass flows are going to be changing, valves are going to be opening and closing, so your oil levels are always going to fluctuate a bit.
Yeah, but like Jörg says, as long as you've got a third of the sight glass minimum, yeah. But any less
in any of the compressors,
in any of the compressors,
not just one.
Not just one.
Oh man,
Great.
that sounds like a wrap.
Thank you, guys. Thank you, guys. It's as usual been a pleasure listening to you guys. It's been you talking today, and that's great. I just want to say to our audience that please go ahead and post suggestions to next themes. If you have any more questions or comments, please post them again, and we'll collect all the questions and comments, etc., and answer as good as we can afterwards. So again, thank you so much for attending, and thank you for listening in on this podcast. And I hope you will have a good a good Christmas and nice and happy New Year to all of you guys out there in the world. Thank you so much.
Thank you.
Thanks. Talk to you.
Thank you.
Yeah. See you.